So, we wrote down two versions of the spectral theorem for a finite family of commuting self adjoint bounded operators. One was the spectral measure form, the other was the continuous functional calculus. Okay. So, we will prove the continuous functional calculus form and use that to deduce the spectral measure form, which is more or less straightforward. And once we have the spectral measure form, you can extend the continuous functional calculus to L infinity functional calculus as we did for a single operator. Okay. So, many of these things will see brief sketches, most of the details can be easily filled up. Okay. So, let us start with the proof. Okay. So, we shall prove that we shall prove the continuous functional calculus form. Okay. So, continuous functional calculus form. Okay. So, we start with the lemma, we need a lemma. So, mainly because many things we need to show that various things commute. Some of this you have seen in some other statements when we did all those C-star algebras and wrote down spectral theorem for C-star algebras. It is essentially the same, but let me write this as a separate lemma, so that we can use it directly. Let A and B, so I take two operators, be bounded self adjoint, if A and B commute. So, if A and B commute, so that is same as A bracket B. So, this is a compact way of writing commutator of A and B, right. So, this is simply A B minus B A. Okay. Suppose this is 0. So, A B minus B A is the bracket of A and B, that is the notation we will be using, that is 0 is same as saying A and B commute. Okay. So, if A bracket B is 0, that means A and B commute, then the same is true for any function of A and any function of B. Okay. So, you take any bounded functions f and g, then I can define f of A and g of B, they will also commute. Okay. So, then for any bounded functions, then any bounded functions f and g. So, once you have bounded functions, you can define f of A and g of B, right. We have the commutator of f of A with g of B, that also is 0. That means, any function of A commutes with any function of B. Okay. So, here self adjointness is something which we will use, because the proof becomes easy. When we go to normal operators, we will see that this is slightly non trivial proof. Well, these are bounded functions. So, I am not saying they are real valued, but we can assume it to be real valued, right. So, well, that is because it is enough to, if I prove this statement for real valued functions, real valued bounded functions, then it will follow for complex valued bounded functions, right. So, let us write f equal to f 1 plus I f 2, okay, and similarly g equal to g 1 plus I g 2. Okay. So, f 1 f 2 g 1 g 2 are real valued, right. I am writing it as real and imaginary parts, that is all, right. Then what is f of A, right. This is a star homomorphism and all that. So, you know that this is linear. So, this is simply, well, if f is bounded, f 1 and f 2 are bounded, g is bounded, g 1 and g 2 are bounded. So, all these things will make sense, right. So, I f 2 A, similarly g of A equal to g 1 A plus I g 2 A. Okay. So, if f 1 f 2 commutes with g 1 g 2, A, then sorry, I have A and B, right, there are two operators. So, this is B and here G 1 of B, G 2 of B, right. So, I want to say F and F A and G B commute. So, F A into G B should be equal to G B into F A. So, if you look at this, if I know that the same is true for real valued functions, then it automatically follows that it is true for complex valued functions, right. So, hence it is enough to prove the theorem or lemma, right, we called it lemma. So, enough to prove the lemma for real valued functions, okay. Alright. So, let us try to prove this for real valued function. What is the advantage of real valued functions? So, let us assume that f and g are real valued. Okay. If it is real valued, then f of a and g of b are self adjoint, right. So, then f of a and g of b are self adjoint, right, because f bar will go to f of a star and f bar is f. So, f of a star is f of a and so it is self adjoint, similarly for g b, right. So, I want to show f of a and g b commute, but now f of a and g b are self adjoint operators and so it is suffices to. So, first let us prove that f of a commutes with b. Okay. So, first that is enough actually. First by symmetry let us prove that f of a commutes with b, right, but that follows from whatever we already know, right, because if a commutes with b, any function of a and b is self adjoint, right, a and b are self adjoint. If a commutes with b, then all polynomials in a will commute with b and so f of a will commute with b for any continuous function f, and then you take pointwise bounded limits and so on and prove that it commutes with b for f of a commutes with b for any bounded function, right. This is something which we already know. Okay. So, this we already know, but now you just repeat the argument, right, because f of a commutes with b, f of a is self adjoint, right. So, think of this as the self adjoint operator, b is commuting with f of a. So, b square will commute with f of a, any polynomial in b will commute with f of a. So, any continuous function acting on b. So, if g is continuous, g of b will commute with f of a and then you can take limits and say that for any bounded function g, g b will commute with f of a, right, whatever we have just proved, right. So, by the same argument, well same argument works because f of a is self adjoint, right. So, f of a is self adjoint, g of b will commute with f of a, right. So, this was one of the things we did while dealing with spectral theorems. An operator commutes with a self adjoint operator A if and only if it commutes with all those operators coming from the continuous functional calculus, if and only if it commutes with all projections coming from the L infinity functional calculus and so on, right. So, it is just that, right. So, now we can prove the continuous functional calculus form. So, we will do this by constructing the continuous functional calculus, that means constructing the homomorphism as in the case of single operator we did some time back using the resolution of identity thing, right. So, if you remember we constructed the Riemann like sums and then proved that the limit exists, right. That is precisely what we will do, but we have several operators here, right. So, we have to be a bit more careful, but the lemma we just proved tells me that whatever functions in A j I take, those operators all will commute, right, because A j's are self adjoint operators. So, and commuting. So, any function in A j, right, any function in A j. So, let us say f of A 1 and g of A 2 or h of A 3, whatever function you take in A 1, A 2, A 3, they will all commute with each other, right. So, we can use that from the lemma, and so various projections we will deal with corresponding to each of the A j's, they will all commute. Okay. And so, we will be doing exactly like the one variable case, except that the Riemann sums will be constructed on product spaces. Okay. So, just to simplify the notation and writing down, for the ease of writing down, we will just take two operators A 1 and A 2 and then develop the continuous functional calculus for that. The same proof exactly verbatim works in the n dimension operator case, except that the notation becomes slightly more complicated. Okay. So, for simplicity, so let us start with that. For simplicity, we will assume that there are only two operators. We will assume that n equal to 2. Okay. So, we have A 1, A 2, right, only two operators, self adjoint and commuting, right. So, A 1 A 2 equal to A 2 A 1 and any function of A 1 will commute with any function of A 2. Okay. Okay. And well, not just commuting, we will assume that the norm is less than or equal to 1. Again, this is not a very serious matter, j equal to 1 2. Okay. Otherwise, you will be looking at the interval minus norm A 1 to norm A 1 cross minus norm A 2 to norm A 2, right. Here we can write just minus 1 cross minus 1 comma 1 cross minus 1 comma 1. Okay. So, it is easier to write, that is all. All the proofs whatever we do will work exactly in the same way, even if we are looking at a product space with the norms as the endpoints. This makes it easier to write it down. Okay. So, we will be constructing the star homomorphism phi A 1 A 2 from continuous functions on this product space j equal to 1 to 2 sorry. Yeah, minus 1 1 cross minus 1 1. So, that is my product space to B of h, right. So, that is how we will be constructing the star homomorphism, and we will do exactly like what we did in the case of single operator, writing down the Riemann sums. Okay. So, we look at the Riemann sums as in the single operator case, right, as earlier. But one advantage is both A 1 and A 2 are self adjoint. So, we have L infinity functional calculus for both A 1 and A 2. Okay. So, note that we already have L infinity functional calculus, for both the operators A 1 and A 2 and A 2, right. So, let us form the Riemann sums. Now, the difference between the single operator case and operators n operators, or here we are looking at only two operators, is that instead of looking at the interval and dividing that into smaller intervals, we will have to look at a square, right, because we have 2 operators. If it is n operators, we will be looking at an appropriate cube in Rn and dividing that into sub cubes. Okay. So, for each n, so I am going to define these Riemann sums, right. For each n, divide the interval minus 1 1. If the minus 1 1 came because we assume that norms of the operators are less than or equal to 1. Otherwise, we will be looking at minus norm a 1 to norm a 1 and minus norm a 2 to norm a 2. Okay. So, making them equal gives me a square, otherwise I will have a rectangle, but the same arguments will work. Okay. So, divide minus 1 1 into equal intervals of length 1 by 2 to the m. Okay. Okay. So, I should write m here. So, that is the mth level, right, but it is not enough to divide one of the intervals, I have to divide both the intervals. Okay. So, if I divide one interval, then I can divide the other interval in the same way and take the product. Okay. So, consequently, divide the square. So, I have minus 1 cross minus 1, right. So, minus 1 cross minus 1 1 cross minus 1 1 into squares of length. So, smaller squares of side length 1 by 2 to the m, right. So, into squares of side length 1 by 2 to the m. Okay. So, let us see what that is. Let me draw a picture so that this is clear. So, I have the square minus 1 to minus 1 1 cross minus 1 1. Okay. So, 0 is actually in the middle. Okay. So, I have minus 1 1 here and 1 is it 1? Yeah, okay, 1 minus 1 and this is 1 1. So, I am in R2 now, I am looking at the square with these coordinates, right. So, that is the square minus 1 1 cross minus 1 1. Okay. So, minus 1 comma 1 as the each. So, the interval in the x direction, x axis direction is divided into 1 by intervals of length 1 by 2 to the m, and similarly on the y axis, right. So, I am dividing this into intervals of length 1 by 2 to the m. So, let me denote one of them. So, this distance is 1 by 2 to the m. Okay. Similarly, here, right. So, on this side. Okay. So, let us say this is 1 by 2 to the m. So, once I do this, I can look at, so let me draw only what I need. Okay. Right. If I join all the lines, I am going to divide this square, the bigger square into smaller squares. So, the smaller square is here. So, this is one square, okay, of side length 1 by 2 to the m, right. The length and the width both are 1 by 2 to the m for that square. So, in the single operator case, we had the interval divided into smaller intervals. Here we have a square divided into smaller squares of same side length. If you have 3 operators or more, you have an appropriate cube, right. You will look at minus 1 comma 1, the n-fold product of that, and each side you will divide exactly into 2 to the m intervals of length 1 by 2 to the m and look at the product, right. So, you will get several these small squares. Okay. In the, so you should know the number of squares sort of growing in the, if you divide one interval into 2, you will get 2 sub intervals. if you look at the square and you divide each side into 2 intervals each, you will get 4 squares, right. In 3 dimension you will get 8, in n dimension you will get 2 to the n and so on. Okay. So, that is 1 square. Now, now the notation is, so this is why I restricted to just 2 operators, because the notation will get cumbersome. So, so we will do exactly what we did earlier, we will form a Riemann sum like this, and then each interval is going to be divided into 2 subintervals of same length, right. So, in one direction you will have that, but there are 2 such directions, right. So, each square will get divided into 4 sub squares. So, keep that in mind. So, if I take one interval of length, so let us say this is of length 1 by 2 to the m and this is of length 1 by 2 to the m. I divide this interval into 2 parts like this, right, and here also into 2 parts like this. So, if I join everything, I will get 4 sub squares, and in 3 dimension I will get 8 sub squares and so on. So, you have to keep that in mind. Okay. It is not all that difficult. So, let us start with the notation again. So, let L equal to 0 plus or minus 1. So, I am going to write down the Riemann sums, right. So, I am just the notation minus 1 1 plus minus 2 all the way to okay. So, let me write this in a slightly better space. Let L equal to 0 plus or minus 1 plus or minus 2 etcetera plus or minus 2 to the m minus 1, okay, and minus 1 minus 2 to the m. Okay. So, up to here. Anyway, you can compare it with the one single operator case to see what we are doing. In that we did not bother about minus 1 1, we looked at minus r to r and then j running from minus 2 to the n r to 2 to the n r, right, when we divided the interval into smaller intervals of length 1 by 2 to the n. That is precisely what we are doing, except that now we have minus 1 1 cross minus 1. And we are dividing the square into smaller squares of side length 1 by 2 to the m, right. Okay. And we look at the projections. So, look at the projections. So, I am going to use the L infinity functional calculus for each of these operators, right, both A1 and A2 admit L infinity functional calculus. So, chi L by 2 to the m comma L plus 1 by 2 to the m. Okay. So, let us say closed here, open here and A1. Okay. So, what is this? The chi L by 2 to the m L plus 1 by 2 to the m is a bounded function, right, it is an indicator function. So, that indicator function of A1, that makes sense, right, because that is a bounded function. If f is a bounded function, f of A1 makes sense, and since chi equal to chi bar equal to chi square, we know that this is a projection, right. We also look at the other projection. So, with respect to A2, chi k by 2 to the m. So, let me use k instead of L there, k plus 1 by 2 to the m A2. Okay. Well, that is a projection, right, and these projections commute, because we already proved that lemma f of a and g b commute if a and b are bounded self adjoint and commuting. So, that is the situation here, these projections commute. So, if you look at the one variable case or the one single operator case, for each interval after subdividing the bigger interval into smaller subinterval, each interval we had a projection, right, that was the difference of the resolution of identity, right, at endpoints. That is precisely what this is, except that for each square we have projections, right. So, note that these projections commute. These projections commute, right, by the previous lemma. By the previous lemma. So, now what we do is for each smaller square we have a projection, right. So, that is like the length of the interval, right, in the Riemann sum, or in the Riemann sum for the square it is the area of the square, right. So, if you did not have chi of A1 and chi of A2, you are simply multiplying the length of these intervals, that is the area of the square, and then you will multiply with the function value at some point and then take the sum, right, that is your Riemann sum. Okay. So, form the Riemann sum. So, for f in C minus 1 1 cross minus 1 1, right, form the Riemann sum or Riemann like sum, right. So, Riemann sum by simply adding up these projections multiplied with the function value, right. So, we will call that phi mf, right, at the mth level, because we divided the intervals on both sides two smaller intervals of length 1 by 2 to them, right, that is the mth level. So, equal to summation over k and l. So, remember k and l ran from some 0 plus or minus 1 plus or minus 2 etcetera up to some point, right, f of l by 2 to the m, k by 2 to the m times those projections, right. So, l by 2 to the m, l plus 1 by 2 to the m A1, that is the first one, and chi k by 2 to the m, k plus 1 by 2 to the m A2. Okay. So, the product of these projections you should think of as the area of the square, right. So, for one square, so let us look at the square. I will draw this slightly bigger. I have so, in this horizontal direction it is L by 2 to the m and L plus 1 by 2 to the m, right. In the vertical direction it is k by 2 to the m and k plus 1 by 2 to the m, right. So, that gives me a square, right. So, that is a square, and f of L by 2 to the m, k by 2 to the m is precisely this point, right. So, we are simply looking at f at some value in that square. In the Riemann sum for interval it would be f at some value either one of the endpoints or some point in the middle, does not matter, multiplied by the length of the interval, right. When we developed the continuous functional calculus, the length of the interval was replaced by the projection, and that is precisely what we are doing here as well. So, just like what we did in the single operator case, we will prove all that we need with these phi m's. Okay. So, one is the limit of phi m will exist as m goes to infinity, and phi m has all the other properties you want, that is it is a star, it preserves the star, phi m of f g will be phi m f into phi m g and so on. Okay. So, we will show that 1 limit m going to infinity phi m f exists in the operator norm denoted by, so we will denote it by phi of f, like what we did in the case of single operator, right. Okay. 2, the phi the phi is going to be our homomorphism, right. So, phi of f g will be phi of f into phi of g, and this will follow from the same property of phi m, right. Phi m is multiplicative, we have seen that in the case of single operator, and that will continue to hold. Okay. 3 phi of f bar is equal to phi f star, right. Again will follow from the property of phi m, and phi is linear of course. So, that is trivial, phi is linear and operator norm of phi of f is less than or equal to the supremum norm of f, right. So, all that will follow. So, we will stop here. All that will follow once we show that the limit exists, because all the other properties are true for phi sub m, and if phi sub m's converge, then all these properties we have written down in 2, 3, 4 will continue to hold, that it is a homomorphism, linearity and preserving the star, right. That is how you get a star homomorphism. Now, how do you show that the limit exists? Well, this again we follow exactly what is there in the single variable case, that the the Riemann sums will converge to the integral, right. So, that is what we will show. Well, how do we show that? We will take two quantities m and l, let us say m greater than l, and look at phi m minus phi l, right, and show that it is a Cauchy sequence. Now, if you recall what we did in the case of single operator, because when L was greater than m, we had to divide the m one interval into further smaller intervals, right, and then we looked at the difference of the values of the function and used uniform continuity, and that is precisely what we will do here. Only thing is, instead of intervals we have smaller subsquares, but the proof is exactly the same. After that, all this will follow and L infinity functional calculus will also follow. Okay. So, we will do that in the next class. Okay. So, let us stop here.